Swayam Prabha. Digital India. Educated India.
Now we will in this lecture we will introduce condensation heat transfer. Then we will also see the different modes of heat transfer, which is film wise and drop wise. So first we will take up the film wise condensation process, and then we will do an analysis of the film wise condensation process, in which we will try to see how we can get mathematical expressions for getting the heat transfer coefficient in the film wise mode. And then lastly, we will take up an introduction to drop-wise condensation process. So let us begin. Now, what is condensation? So this is a common name which you all know. Condensation is the change of state of matter from gas phase to the liquid phase, or vapor phase to the liquid phase. And the reverse is called as vaporization. So condensation and evaporation or vaporization, these two are processes which are, let's say, the phase change processes from vapor to liquid is condensation, and liquid to vapor is vaporization or evaporation. Now, when does this happen? Condensation occurs when the temperature of the vapor is reduced below the saturation temperature. So the vapor can be available at different pressures, and as you know, at every pressure there will be a corresponding saturation temperature wherein phase change will start. And when you bring the temperature of this vapor or a gas below its saturation temperature at the given pressure, then of course the phase change will begin. Now there are common modes of condensation. So for example, you have the film wise and you have the drop wise. These are the two common modes. Now these two are also they are also called as heterogeneous condensation, because you require a solid wall, an interaction of this vapor or the gas with a solid wall which is kept at a colder temperature. And then depending on the properties of this wall and depending on the other thermophysical boundary conditions, the condensation may be like film wise, or it can have the drop wise condensation. There are also instances when homogeneous condensation takes place. That means it doesn't require any solid this thing. You just cool the vapor and volumetrically the vapor will convert into liquid, which is called as the homogeneous condensation. We are not going to study that in this lecture. We are going to study heterogeneous condensation, which is a more common example in many engineering applications. There are also direct contact condensation, which can also take place when, for example, a liquid is sprayed in a vapor medium. In this case, the vapor will condense when it comes in contact with this liquid, colder liquid. Or the other way around, when a vapor is getting ejected from a pipe, for example, and this pipe is inside a liquid, then also condensation of the vapor will take place. But we are not going to study this. We are going to focus our attention on these condensate films in the film wise mode and condensate droplets in the drop wise mode of condensation. So now let us look at these two very specific cases which are of most common interest. The film condensation, when the condensate wets the surface and form a liquid film, as you can see in this particular diagram, schematic diagram. When there is a film, and this, because of course if the gravity is acting in a downward direction, then the film will actually flow down, and as the condensation keeps occurring, more and more liquid will get condensed over this interface, and therefore the film thickness will grow. And in the later part of the lecture we will see how to analyze this particular film growth. The surface gets blanketed by a liquid film which serves as a resistance to heat transfer. Now the heat has to get transferred from here because it is vapor here, and liquid gets converted. So the latent heat which is generated, that has to pass through this particular film, and therefore as you know, most liquids are low thermal conductivity fluids, and therefore this gives a resistance to heat transfer, and this is what we will try to analyze in the later part of the lecture. Now, as I just told you, condensation can also occur in a dropwise mode in which distinct drops like pearls gets formed, as you can see on this particular figure. And they slide down if the gravity is again in this direction. The droplets may slide down, and as the droplets slide down, they will coalesce with all the droplets which are coming on their way, and they will try to clean the surface. As you can see here, some drop has been removed and the surface has become clean, and then new drops will start forming, new nucleation will start, in these locations. So what is usually seen is that in such a case there is no liquid film in this particular mode, and the heat transfer rates are very high, in fact, as compared to the film wise. So this is in a way much better heat transfer process, the dropwise condensation, as compared to the film condensation mode. So let us move on to the next slide, number 5. Now here we will start looking first, as I said, into the film-wise mode, in which there is a distinct liquid film which gets formed because of the condensate liquid. And because of the gravity, as I said, the gravity is acting in this direction, for example, G. So the liquid film, as you can see, will start growing. Now, the cold plate is on the left hand side. This is the cold plate and this is the vapor. The gravity is acting downwards, and the latent heat has to be released now. So there, at far away from this particular film, the vapor may be at a temperature which is TV infinity. And then naturally it has to become Tsat at the interface, because the phase change has to start. And then the heat has to go towards the colder surface, which is maintained at a lower temperature, T surface, which is lower than the vapor temperature, and you will get a thermal boundary layer, which of course the film is also flowing down. So there is in real time, in real conditions, there will be a nonlinear, let's say, variation of temperature because of the combination of conduction, heat transfer through the film here, and the convection which is taking place because of the film movement downwards. In a similar way, if you see the velocity profile, you will have some uy of the vapor. There is some vapor velocity, and then there is a liquid velocity, and then there is an interface condition here at the interface, and in real conditions you will have a vapor velocity, the liquid velocity, the film is flowing down, and you will get a velocity profile. Now the question is how to get this temperature profile and how to get this velocity profile. This is what is the most important part, because this will, once you have these two temperature and velocity profiles, then one can actually analyze the entire heat transfer process in this film wise mode of condensation. So please note all the important terms here. The temperature of the condensate is Tsat at the interface. It decreases gradually to Ts. I just told you. The surface temperature is Ts, which is maintained here. The latent heat has to be released. And of course, if the vapor temperature is higher, then there is some subcooling. The vapor temperature will first come from TV infinity to Tsat, and so that will be a sensible heat transfer, and then latent heat. Of course, as we go along, we will see that we will make some assumptions which will make the analysis simpler. Otherwise, to include all this details, the model will become quite complex. So first we will in this lecture we will take up a simple model which through some assumptions we will try to simplify the process. So now, as you will realize, that this particular liquid film is falling down, and it will remain laminar. Of course, this particular interface is never smooth. There will always be some ripples, and these ripples will increase the surface area which is exposed to the vapor. So you can see this is the vapor and this is the liquid which is falling down. The heat transfer is taking place in this direction, and the temperature is maintained here, Ts. And there is the vapor temperature. So what is usually observed if this plate, vertical plate, is long enough, then you will have a thin film which is flowing, there will be ripples on the surface. If there is interfacial shear which is taking place at this interface because of the velocity of vapor and velocity of liquid interacting with each other, so this is a shear zone, provided of course the viscosities of the liquid and vapor are substantial, and the vapor velocity is also substantial. Then you will have the shear stress which will be generated by the movement of the vapor and the liquid, which is having a relative velocity with each other. And as the interface shear force decreases with film thickness, and it also increases the heat transfer, because if there is a shear and the film becomes thinner, then of course the resistance to heat transfer will go down, and therefore you will have let's say lesser. So thinner the film, the better it is for heat transfer. Thicker the film, it will give a resistance. And then what is also interesting is that as more and more mass gathers up, this will be like rho L um into P delta, where P is the width perpendicular to the plane. It can also be in some books it is mentioned as B or P, either of the two. So you will see that the film will become turbulent eventually. So the film passes through, if this plate is long enough, then the film passes through laminar region, and then there is a wavy laminar or a transition region, and then eventually a turbulent region. Now, how do you differentiate between this? One can define a Reynolds number, so which has a length scale and a velocity scale. The velocity scale is of course given by the velocity of the film which is falling down, which comes from the mass flow rate of the film, and one can define rho vd by mu, and then instead of the diameter, we can put the wetted parameter, the area of the wetted area divided by the wetted perimeter, and then the velocity can come from the mass flow rate, and therefore you can define the Reynolds number of the film, which is Re delta, as 4 m dot by P into mu L, and this value, when it is of the order of 30, the flow is typically laminar, and then as it becomes more and more, eventually at about a Reynolds number of about 1800 or so, one can start getting turbulent films, and this is typically taken as the demarker between the laminar flow, and between 30 and 1800 it will be typically a wavy laminar or a transitional flows, and beyond Re delta equal to 1800 you will see that the film becomes fully turbulent. So typically in engineering applications you will have mostly turbulent flows or wavy laminar transition flows and turbulent flows, and then in this particular lecture we will see how to analyze them. Now, one more practical consideration which is usually there is that you have instances when you have pure vapor condensation, but most of the time in real-time applications you will have some non-condensable gas, like for example in steam condensation on the cold surface in the presence of air. The air is a non-condensable gas. So now naturally you know the Dalton's law of partial pressure. So it's a mixture of vapor and air, and therefore the vapor is actually let's say exerting a pressure which is equivalent to its partial pressure, and therefore the condensation will start when you have the dew point hit. I hope you remember the fundamentals of psychrometry. And as the temperature of the cold wall will start becoming colder and colder, you will see that it will become let's say the dew point will be hit when the temperature becomes lower than the saturation temperature corresponding to the partial pressure now in this case, because you have a mixture, and therefore what happens is that now you are dealing with actually three boundary layers. One is the vapor, and you have the vapor and air mixture here, and then close to the wall you will have a liquid film which is falling down, and there will be a region here which will be like it will be like a region which will be depleted. It will be more of air, and less of vapor because the vapor has condensed, and therefore you will have a film which is more concentration of air than the mixture here. The far away there is a mixture, but close to the interface you will have air enriched. Let's say if it is air and water vapor, then you will have an air enriched region which will be creating an extra resistance to the overall heat transfer. So what happens is that because in this region it is depleted by vapor, the partial pressure of vapor near the interface decreases as compared to the ambient, and this reduces the saturation temperature of vapor at the interface, and therefore eventually you will see that the diffusion layer through which now this vapor has to pass through this extra resistance to reach the interface and condense there, and because of the change in the partial pressure close to the wall, close to the interface, you also get let us say an added resistance for diffusion of this vapor towards the interface, and the overall heat transfer will always reduce. So please note this fact more or less, that in the presence of non-condensable gases, because of the presence of a liquid film and a gas boundary layer, so there are now two let's say distinct boundary layers. One is the liquid film, the one is the area which is more in gas concentration than the vapor. That means if it is air vapor, then more air will be there close to the interface, and this you will also appreciate that whenever vapor condenses, the volume of the vapor will suddenly become less because the density of liquid is very high, and if one unit volume of vapor condenses into liquid, the liquid actually occupies very little space, very little volume, and therefore there is a sort of a suction which is created close to the interface here, and this also induces some velocities close to the interface. So this type of let's say film condensation in the presence of non-condensable gases is again an area of study. We will not go into the details in this particular lecture, but in many practical applications, including power plants, you have situations where the water vapor and air mixtures are usually present. Also in the atmosphere, whenever condensation happens or dew forms or fog formation happens, you will always see that the heat transfer coefficients are lower than if it would have been a pure vapor. So that is also you have to note this point. We will not go into the details of analytical details of this particular type of condensation in the presence of non-condensable gas. However, what is important for you to know is the typical physics close to the interface, which I just explained, and the fact that the overall heat transfer will reduce because of this additional gas boundary layer which gets formed close to the interface. So this is another cartoon. It always, as I said, has a detrimental effect, and all these vapor molecules will when they condense, these vapor molecules, which are the black spots, they will all get condensed here, and then as soon as they condense, there will be a gas boundary layer which will be let's say less concentration of vapor molecules and more concentration of the gas, non-condensable gas molecule, and that will create an additional boundary layer at the interface. Even small amounts of this gas in the vapor will cause significant drop in heat transfer coefficient. Please note that. So whenever you do calculations for pure vapor, please note that if there is a non-condensable gas, either by design or by situation or by the fact that you are not able to have clean vapor, some gas, some non-condensables are there in the vapor, then your actual heat transfer coefficient, which will be observed in the practice in the engineering application, will actually be lower than what you have calculated or estimated by a pure vapor condition. So the vapor phase velocity affects the overall heat transfer coefficient when NCGs are present. Also, if there is a strong vapor velocity here, in this region, then the boundary layer thicknesses will be affected, and it can also have a depending on which direction the vapor is flowing, you may have a detrimental effect also because of the presence of these velocities in the gas phase. So this is only for you to remember. We will not do analysis, as I said, of film-wise condensation in the presence of non-condensables. So now let us look at some practical applications of such a film-wise situation. So it can occur over a vertical plate, for example, as we were just discussing. It can also occur on vertical cylindrical tubes. For example, cold water may be flowing inside this pipe, and this pipe is subjected to a vapor outside, steam, for example, and gravity, if it is acting downwards in this direction, then you will see that the film is formed around the cylinder, which is kept cold by some internal flow of liquid. That can also be one of the applications. It can also be horizontal in this direction, so the pipe may be inclined vertical, or it can be inclined horizontal, and then you will have horizontal cylindrical situations, or vertical cylindrical situations, and in each case the value of P is given, which is the wetted perimeter. The area of the film is L into delta. In this case, this is the L into delta. And similarly, in a cylindrical thing, it will be pi d into delta, and that will be this particular area. And if it is a horizontal cylinder, then it will be 2L, where L is the length of this thing. So that will be this particular area which is marked here. And then the hydraulic diameter can be found out by 4 AC upon P. Similarly in this case, so in all the cases you will see that the hydraulic diameter comes out to be 4 times of delta. Now, if you have a series of cylinders or series of in a typical heat exchanger, you have seen in the earlier lectures the arrangement of a shell and tube heat exchanger, for example, and if it is used for condensation duty, then the vapor will be in the shell side and the cold liquid will be flowing inside these tubes, and you will see that the vapor condenses, and then the liquid falls down. And this is also helpful because depending on the distance, depending on the rate of condensation, you may have droplets which are falling down, and they are made use of because this falling droplets will disturb the boundary layer here at the lower position, and similarly more and more liquid will keep falling down in this heat exchanger, and you will eventually see that the heat transfer actually increases because of this continuous bombardment of these droplets, tiny droplets or liquid films which are falling down from the top cylinder to the bottom cylinder. So these are various applications of film-wise condensation. And the analysis becomes simpler if you have geometries like vertical plate or a horizontal vertical cylinder or a horizontal cylinder, and that is what we will take up next. It will be the film-wise condensation on a flat plate, on a vertical flat plate. So this finishes, this brings us to the second section, which is the laminar film condensation on vertical plates. So we will do the Nusselt analysis, which was proposed by the German scientist Nusselt, and it is attributed to him. So this is slide number 10, and we are in section 2 now on condensation heat transfer. So let us begin our activities to understand and analyze laminar film condensation. So as we just said, there is a plate, there is a vertical plate. This is the vertical plate. Both the plate and the vapor are at constant temperatures, which is Ts and T vapor at far away. Temperature across the liquid film varies linearly. So now this is an assumption. So as you will recall, in reality there is conduction. There is conduction heat transfer happening in the film, and there is some convection also taking place because of the downward movement of the film. But we will assume because of this superposition, there may be a nonlinear temperature profile which is shown here. You know, so this particular film we will not consider because it will become difficult to analyze. So what we will do is we will convert this into a simple model where only conduction takes place. And as you know from Fourier's law of conduction, because of which if pure conduction is assumed, the convective component is neglected as compared to the conduction component, then you will have a straightforward linear temperature profile, and that will be easy for us to sort of model and get estimates of. So our aim is of course to get the film thickness, get the velocity profile, and now for the velocity profile also we will make an assumption that there is no vapor velocity. So if the vapor velocity is neglected, then you will have a straightforward condition like this, a second order velocity profile, in which because there is no velocity of vapor, there is no interfacial shear, and therefore if when the velocity of vapors are low, the del u by del y at y is equal to delta is equal to 0. That means this is like a 90 degrees here. Let me make it once again so you can see that this gradient is 0, and therefore this particular thing is a 90 degree here. It's normal to the interface, and this essentially means that there is no shear stress, because the shear stress, as you know from the law of viscosity, that its tau is proportional to mu into del u by del y at y is equal to delta. And since del u by del y at y is equal to delta is assumed to be 0 because there is no interfacial shear, because the vapor velocities are low or 0, that is what we are assuming, and therefore there is no shear interaction. So because of this boundary condition, the analysis will become quite simpler again. The other boundary condition is of course at the wall, which is the no slip boundary condition here. So you know the temperature is Dirichlet boundary condition, which is Ts, the surface temperature, colder surface temperature at the vertical wall, and the saturation temperature at the interface here, and the fact that only conduction heat transfer is assumed. This leads to a linear profile, and then the flow of condensate is also laminar. We will assume that we are doing only in the laminar region, so the turbulent region is neglected, and that is why here we are only the convective component is actually neglected here, and the liquid properties are constant. We will not assume that the K is a function of temperature or something like that, or mu is a function of temperature. And lastly, the assumption is that the acceleration of the condensate layer is negligible, which essentially means that the film is flowing down, and all the forces are the summation of the forces is becoming 0, because this particular acceleration is supported or is resisted by the shear stress. Eventually, we will assume that there is no acceleration which is taking place. So the velocity remains constant of the particular liquid film at a given point. So under these assumptions, now we can apply the Newton's second law of motion, because there is no acceleration. The weight of the film is fully supported by the shear force and the buoyancy. So here you can see the free body diagram, in which you can see that the weight is acting downwards, and now we can take the weight of a particular element here from the geometry and the mass and the rho, the density of the fluid. So if you equate the summation of downward forces to the summation of upward forces, you will see that the downward forces is dominated by the weight of the element, which is trying to pull it downwards, and the shear stress is the friction because of the viscosity and the wall. There is a shear stress which is trying to oppose this particular motion, and of course there is buoyancy, because this particular fluid is a heavier fluid kept in a lighter medium, which is the vapor around it. and the fact that our boundary conditions are simpler. We have already assumed, we have already discussed these velocity boundary conditions, two velocity boundary conditions and two temperature boundary conditions, no slip and specified temperature. And with this, if you equate the forces in the downward and the upward direction, and because now you can apply the Newton's second law, you will see that the weight is equal to viscous shear force plus buoyancy force. And if you substitute the weight, the shear force and the buoyancy force, and then integrate from y is equal to 0 where there is no slip, that is what we have just said here, and at y is equal to delta where you have there are no shear stress or interfacial shear stress at the interface are assumed to be negligible. And if you equate this and apply the Newton's second law, you will see that you get the velocity profile. So this velocity profile starting from y equal to 0 to y equal to delta at any given position, you can find out. So this is the way the velocity profile is calculated, and the velocity profile comes out to be g delta rho divided by mu l into y delta minus y square by 2. So if you apply this particular velocity profile, now you can, since the density is constant, you can get the mass flow rate. So the mass flow rate of the condensate at any location where the condensate film thickness is delta, you can integrate the velocity profile rho AV. So this is applying the continuity equation. We can get the mass flow rate of this particular. So you can perform the integration at your home, and you can get the mass flow rate of the condensate. So now we know at any location, what is the mass flow rate of the condensate where the delta is known. Now the only thing is the delta is not explicitly known, so that can also be now determined. Because we can now, the rate of condensation is given by the derivative. So dm dot by dx will depend on the d delta by dx, and we also know from the energy equation that the amount of heat which is passing through dq dot is equal to the dm dot, which is the small amount of mass which has been condensed in each layer in the x direction, and multiplied by the latent heat. Now why latent heat? Only the latent heat because we have assumed that the interface temperature is T saturation. So now this can be equated with the Fourier's law, which is minus Ka dt by dx. So this is the K, this is the area, which is B into dx. So B is the dimension in the depth of the plate, and then T sat minus Ts divided by delta. So this is the gradient of the temperature at the interface where we are calculating the dq dot, and from there one can calculate the dm by dx. So now we have two independent expressions of dm by dx, one coming from the continuity equation and the other coming from the energy equation, and now these two can be equated together to get the governing equation of delta. So this is the governing equation of delta, and which we can now integrate to get the film thickness variation. So this is the analysis. So analysis starts with the fact that you have some assumptions. The main assumption is that the acceleration is 0, and therefore you can apply the Newton's second law. Once you apply the Newton's second law, you get the velocity profile, and then you multiply it by rho into A and integrate it. So you will get the mass flow rate of the condensate. Now this velocity and the mass flow rate, they are in the form of delta, and we do not know delta, so we need one more equation, and that equation is the energy equation, which we have just applied here. And both these energy equations and the continuity equations will give you an independent expression of dm dot by dx, which is the rate of condensation. And if you equate the two, you get the governing equation for delta. That is how the delta varies, because the delta is a function of the film thickness is the function of the location. It is also the function of the delta T which has been applied, that is Ts and T saturation and Ts, and of course the thermophysical properties of the fluid and the latent heat which is there, which comes from the energy equation here. So we get the governing equation of delta, and if you integrate the differential equation for delta, you will get the unique expression for delta, which is the variation of the film thickness. And as you can see, it varies at x to the power 1 by 4. So mind you, the x is the location along the vertical plate. So here you get the full picture. This is the x. So at each location we have now we know the velocity profile, we know the mass flow rate, we know the boundary condition, and the linear expression is very simple, because once you know the delta, you know the gradient of the temperature at that location. Because along the entire length of the interface, the temperature is going to be Tsat. Okay, so that, but of course the delta is going to change as you go along the x direction. From here we can now define the Nusselt number, which is, as you know, it is Hd by K, and this is the local Nusselt number along the plate, and one can now know the substituting the expression for the film thickness in the expression for heat transfer rate, we can get the Nusselt number. Please note the form of the Nusselt number. The Nusselt number, again, now it's a function of x to the power 3 by 4. It is also a function of g, the gravity, because that is on the Earth gravity conditions. It's a vertical field. So mind you, if you want to do, let's say, condensation in space or condensation on moon, for some applications, then the g there will be different, and the rate at which the film will grow will be different, as you will appreciate. And then once you know the local Nusselt number at each location here in this point, each location, then one can always integrate it along the length and get the average Nusselt number. So this is Nu bar x, and this is Nu x, which is this is the local value, this is the local value, and this is the average value, along the entire plate. So when you have to design, you can take the average values, rather than the local values. But if you want to know the local variation, then of course you have the equation here of Nux. Okay, so this provides the framework for getting the velocity profiles, the mass flow rate, the local Reynolds number, the local Nusselt number, and the average Nusselt number. Now, of course, as we have noted down, the vapor temperature may not be saturation, so it may be a little bit higher than saturation. So some amount of sensible cooling will also take place of the vapor, and therefore a small correction may be needed. And this correction is done usually by a simpler method where you have the HFG star. So you use the corrected value or the modified latent heat of vaporization by just adding a portion of the sensible heating, sensible cooling which takes place in the vapor phase. So instead of HFG in the main equation, you can use HFG star, and then get the same value of heat transfer coefficient. Everything else remains the same. You just change the value of HFG with HFG star. Now the liquid may also get eventually subcooled. It may not remain saturated because you have a long plate and the film is slowing down, and slowly some amount of sensible heat will also be taken away. So CP vapor TV minus Tsat and CP liquid, both may be possible. So one has to sort of add that also to the HFG, because the total heat is not only latent heat but now some sensible portion also, and therefore the liquid part, the liquid subcooling part, and the vapor subcooling part both have to be added, so that the HFG star definition will change and you will use the corrected value of the latent heat rather than the pure latent heat. Some sensible component are also added. Please note that since the temperature is changing, you need a reference temperature for measurement of the temperature or for estimation of the thermophysical properties. So all the properties of the liquid are to be evaluated at the film temperature, which is called as the saturation temperature plus surface temperature divided by 2. So this is the average temperature at which all the thermophysical properties will have to be calculated. only the HFG and the raw vapor are to be evaluated at saturation temperature. So this will keep the errors in the estimation to a minimum. Okay, so this is how you will calculate. So this slide number 18 is just a compilation of all the results, so which will be handy for you when you are solving equations. So you have the velocity profile, you have the mass flow rate, you have the local heat which goes into a small section, and then the variation of the film thickness, and from there the local Nusselt number and the average Nusselt number, and then finally the Q condensation and the HFG star, which we have just introduced in the last slide, which is the modified latent heat if the vapor is at a higher temperature than the saturation, and if the liquid gets subcooled also in your system, then you have to use this. Otherwise, you can use HFG as only the latent heat, the pure latent heat. And then the Reynolds number of the flow of the film at any given location, which can also be related to the mass flow rate, because that's what we did in the last slide. But the mass flow rate is also related to the heat, and therefore if you know the heat transfer rate, you can also get the Reynolds number. And remember, this particular Reynolds number will also help you to check whether it is laminar flow. All these results are for laminar flow. For turbulent flow, the heat transfer will be slightly larger, and then empirical correlations or semi-empirical correlations are available. For example here, for example, if you are operating in the wavy laminar region, in the range when the Reynolds number is between 30 and 1800, at that time there are some correlations which you can note down. These are semi-empirical type of correlations which are available. So if you know the Reynolds number of the flow, directly you can get the heat transfer coefficient. There are also some empirical type correlations which are here, like H vertical in a wavy condition is 0.8 Reynolds to the power 0.11 into H vertical smooth. So you assume that the flow is smooth, you calculate the H vertical smooth, and then just increase it by a factor which is this one, which will give you the wavy let's say flow. At this for this equation, the Reynolds number is also calculated by the expression which is given below. So these are some of the different types of expressions which are available. The Nusselt analysis is only valid for laminar flows, which is in the region Re delta of the order of 30 and not exceeding that. Once you exceed, then you can use some of these correlations which we have just discussed on slide number 19. Similarly, when your flow becomes turbulent, now the flow is completely turbulent, and here again you have these correlations which are commonly available. These cannot be derived from first principles. These are mostly empirical or semi-empirical in nature, and one can use them for calculating the heat transfer in turbulent flows. So you can do some of the exercises which we will provide, and then use these correlations to get a feeling of typically the film Reynolds number, the heat transfer coefficients will be quite high in film-wise mode. Naturally, as I said in the earlier part of the lecture, drop-wise condensation will give still higher heat transfer coefficients. However, film-wise condensation also gives quite high, let's say, heat transfer coefficients, and it is a very efficient mode of heat transfer. Of course, in a film-wise, this particular thickness of the film, that is the major problem. The heat has to pass through. That means the vapor which is present here, it has to get the latent heat out at the interface, and this heat has to travel through this thickness of the liquid film. And usually, as I said, the liquid films are having low thermal conductivity, and therefore this conduction through the film becomes the most crucial limiting factor. So as the film thickness increases, you have seen in the expression that the heat transfer actually reduces. So if the plate is inclined, then of course you can use the g cos theta, or the vertical in cos theta. The equation developed for vertical plates can also be used for film condensation on the upper surface by converting it into g cos theta, and therefore equivalent expressions for h, the heat transfer coefficient, can be found out. Now, just a note on vapor velocity assumption. It was assumed that the vapor velocity was small, and therefore the drag due to the vapor flow exerted on the liquid film is assumed to be negligible, which is usually the case. But as we have seen that when the vapor velocity is high, there will be interfacial shear stress, and we will see some of the examples of this also taking place later on when we do thermosiphons. If the vapor flow downward, that is in the same direction of the liquid, this additional force will increase the average velocity of the liquid and thus decrease the film thickness. And therefore, this in turn will decrease the thermal resistance of the liquid film and thus increase the heat transfer. So please remember that the velocity of the vapor can be either in the supporting to reduce the film thickness, or if it is an upward flow, then it has the opposite effect. The vapor exerts a force on the liquid in the opposite direction of the flow, which will thicken the liquid film and thus decrease the heat transfer. So in general, we have assumed the vapor flow to be negligible, but in reality it does affect the film thicknesses because of the shear stress which is caused by the relative velocity between the vapor and the liquid, and this will either increase or decrease the heat transfer depending on the direction of this shear. There are also methods to increase the film-wise condensation or enhancement techniques, because we have seen that this film thickness is the most critical part, that conduction in the film, and therefore if you have the solid which has some features, morphology like what I have shown here, then one can reduce the film thickness at these corner points. And this corner points can become the seat where the heat transfer coefficient can be locally increased. Or you can go for drop-wise condensation, which we will take up next. As I just said, that drop-wise condensation is much better than film-wise condensation, because there these films are not formed and therefore the resistance to the flow is quite low. And how do you do that? One has to make sure that the wettability of the particular fluid on the solid is poor, and therefore your contact angles are more like this rather than like this. So this is the non-wetting surface, this is a wetting surface, and if there is non-wetting surface, then it will lead to usually drop-wise condensation. And the surfaces can be made non-wetting by putting some promoters layers or low surface energy polymers or things like that. Or you can use some vibrations or vipers or electrostatic fields to get rid of this liquid which is formed. You can also do by putting some wires on the tubes. So if you wound wires on the tubes, like this, then this, because of the capillary action, you will have a reduction of film thicknesses here, and this local area you will get a very high heat transfer coefficient. The film thicknesses will be low. So these are some of the methods of enhancing the heat transfer in the film-wise mode. So one way is to go towards drop-wise condensation. The other way is to create some surface morphology so that the film thicknesses get locally lowered, and then you will get better heat transfer. So let us come to the last part of this particular lecture on drop-wise condensation. So as we have noted, in a drop-wise condensation process, there are no liquid films. So this happens because the substrate on which this particular condensation is taking place, the substrate is non-wetting, and therefore the liquid forms like a hydrophobic. It's a hydrophobic drop which gets formed on this substrate, and therefore because of which drop-wise condensation is possible. Now this hydrophobicity is brought, as we have noted, by doing some coating on this particular substrate. Numerous distinct drops of different sizes get formed, as you can see here. Some drops are old, which are already formed some time back and they are growing. Some drops are new. They are just being formed, they are just got formed and they are also growing. So various generations of drops can be seen on the substrate. They get formed on certain nucleation sites, specific sites on the substrate. They grow either by direct condensation because these drops are exposed to vapor on the other side. So vapor will directly condense on these drops and the drops will slowly grow. The drops can also coalesce because, as you can see, this drop is very close to the other drop, and as the drop is growing, it is actually merging with the other drops. So there are two drops which are side by side like this, and when this drop will grow together bigger, then they will merge and they will form one single drop. Okay, so drops are growing by condensation as well as by coalescence of the side drops which are there around them. Now, as you know, this particular coating which is there, which makes it hydrophobic, this is a challenge, how to keep it hydrophobic for a long time, because after a while these coatings get eroded, they get, destroyed on the substrate, and then the hydrophobicity doesn't remain like that, and then the drops will not form, and therefore it will tend towards film-wise condensation. So how to create, engineering substrates which are hydrophobic in nature, and this hydrophobicity is sustained over a long period of time is been a challenge from quite some time. So let us see a video of the dropwise condensation process, and with increasing time we will see different types of droplet distribution. So you can see in the beginning drops are being formed on the screen. You can see the dropwise condensation process, and this is in real time, and you can see the drops are not only growing by direct condensation, but there is a lot of coalescence taking place. Now in the beginning there were small drops which were formed on the entire surface. As the time is proceeding, you will see that bigger drops are getting formed, and I will now make the video a little faster, and now you can see bigger drops which are formed, and these drops, they are coalescing, and then surface tension is making them as circular as possible. They are trying to minimize their surface area. And then when the virgin areas are formed, you can see new drops being formed there in these zones. And then let me go a little bit more ahead, and now you can see still bigger drops are getting formed. And they are growing slowly now because the heat transfer has reduced through the larger drops, because as you will appreciate, the thickness of the liquid is now high and conduction heat transfer is difficult. And in the new virgin areas, new drops or new generation of drops are being formed. And as we proceed further, you will see that drops are becoming bigger and bigger. Surface tension is trying to make them as round as possible. And new areas are getting exposed to vapor, and these new areas, new small drops of the new generation are being formed. So simultaneously there are old generation, the last generation, and you can now see one drop has been fallen down because of the fact that this substrate is inclined, and you can see again new areas getting formed. So in the beginning, there were a large number of small drops, and at the end you will see that there is an ensemble of large drops and small drops. So the morphology of the drop sizes, or the histogram, if you plot, it is changing with time. So initially you have a lot of small drops which are covering the entire surface, and in the later part you will have large drops like this, and then some of the drops have moved, creating these virgin areas like this, and then small drops will start forming here also as the time proceeds. So this is the cycle: formation of initial drops, followed by growth due to direct condensation, followed by growth due to coalescence, and followed by the departure from the substrate. So some of the photographs of this particular process is shown here, and we will also see how coalescence of two drops from the side view. You can see here the drops will coalesce. and now you can see the coalitions process, and this is how the slow motion of the coalitions process takes place from the side view of this particular. So if you see the data for dropwise condensation, as we have noted, the data will typically be higher than the film-wise mode, and you can see the film-wise already is of very high order, 10 to the power 5 watt per meter square Kelvin, and this is still more, one order of magnitude higher. Mind you, this is a log scale here. So you can see that dropwise condensation typically gives very high heat transfer coefficients of the order of 10 to the power 6 watts per meter square Kelvin. But if you see a large amount of data by many researchers, there is also a lot of scatter in the data, and this is because it is very difficult to do experiments because the delta T between the wall and the fluid usually is very small, and therefore this leads to a high heat transfer coefficient. So there are a lot of uncertainties in the data, and the heat transfer also depends on the wetting conditions and the wettability of the fluid, and therefore typically the data will be varying quite a lot. However, in general, please note that dropwise condensation will give very high heat transfer data. So to summarize, dropwise condensation provides extremely high heat transfer coefficients, usually higher than film condensation process. In this process, it involves the formation of numerous distinct drops. It is statistical in nature to a certain extent. There is a quasi-steady state which comes. After a while, bigger drops are formed. They keep falling. The newer areas are exposed. Then new drops will be formed in those areas, and the cycle will continue. The ensemble of these drops, they grow, they coalesce, and they fall off or slide off depending on the orientation of the substrate. You must have seen that such type of drop ice condensation in your home also, sometimes on glass panels, sometimes on PET bottles. These drinking mineral water bottles, you can also see if they are partially filled and kept in the sun, you will see drop ice condensation taking place. So sustaining it is a problem. It is not a trivial problem. Industry has been trying from quite some time to control drop ice condensation process so that the hydrophobicity is maintained. However, after a while, after continuous cycle of drop ice condensation process, this particular film, it breaks down, or this coating is eroded, and therefore the drops may not form, the hydrophobicity is lost, and then you can get back to film-wise condensation mode. So in industrial sector, large industrial sectors, it is mostly film-wise because after a period of time, the hydrophobicity of the substance gets deteriorated, and the physical morphology or the chemical coating which you have done to enhance drop-wise condensation, that is not sustainable, and therefore you go back to film-wise condensation. So we have seen in one lecture the evolution of the nuances of condensation process. We have analyzed the film condensation, laminar film condensation, with analytical expressions for velocity and velocity profile and temperature profile, and then the heat transfer coefficient. But for wavy laminar or turbulent films, we have seen some semi-empirical and empirical correlations for film-wise condensation. And in drop-wise condensation, we have only noted the nuances, the characteristics, and with the fact that drop-wise condensation heat transfers are usually one order of magnitude larger than the film-wise condensation process. It is a very important heat transfer process in power plant engineering, for example, in nuclear energy, in metal purification processes, and so on. So this is something which is quite prevalent in the industry. So with this, we close this lecture on condensation heat transfer uh, at this stage. Thank you. So thank you very much. And if you have any questions, please don't hesitate to ask me. Thank you.